Hi, I'm Stephen. I'm host of two podcasts, The History of the Papacy and Beyond the Big Screen. The aim of both of these podcasts is to dig into the backstory and contexts of the popes of Rome, Christian church, and the interesting bits and the real story behind movies. I'm always interested into diving deeply into subjects to learn more about them and make connections. That is why I love Chad's Scientific Odyssey. Chad makes very complicated concepts of science and the background behind the science and scientists accessible and entertaining. If you want to learn more about my shows, you can go over to my website, a2zhistorypage.com, to learn more. Thanks and enjoy the Scientific Odyssey. I know I will be.
If you were to look at the human body at its most elemental level, you'll find something that's actually pretty surprising. Nearly 99% of its mass is made up of just 60 of the roughly 90 naturally occurring elements found on the Earth. The greatest portion comes from oxygen, which accounts for 65% of the mass of a human being. Next up is carbon, weighing in at 18.5%. Following these two are hydrogen at 9.5%, nitrogen at 3.2%, calcium at 1.5%, and finally, phosphorus at 1%. Everything else, from the iron that gives your blood its red color when combined with oxygen, to the sodium and chlorine that makes that blood taste just a bit salty, all of that together amounts to just 1.3% of your body's mass. Now this changes a bit when you look at the breakdown by number of atoms instead of by the mass of those atoms. Now it is hydrogen that is in the majority, with 62 out of every 100 atoms in your body made of hydrogen. This is followed by oxygen at 24%, carbon at 12%, nitrogen at 1.1%, and both calcium and phosphorus at just a mere 0.22%. The difference in this amount by mass and amount by number of atoms is due to the fact that if carbon has a mass of 12 units, hydrogen is only about 1 unit, with nitrogen being 7 and oxygen 8. Since the majority of what makes a person is water, there are twice as many hydrogen atoms as oxygen atoms, but they only have about a quarter of the total mass. What you may notice is just that 4 elements, hydrogen, carbon, nitrogen, and oxygen, make up most of the body. This would be the case, though the percentages would change, even if water were excluded from this count. This is because most of the molecules in the human body are what are known as organic, meaning that they are a combination of carbon with one or more of the other 3, along with perhaps some of the trace elements, at least in many cases. These organic molecules, many of which are wonderfully complex, make possible all of the self-replicating chemistry required for our bodies to do all of the things that they do. More broadly, we could have done a similar analysis for almost any other life form on Earth, and we would have come up with a similar set of percentages. One of the most interesting sets of questions in biochemistry is why is this the case? And why do these atoms arrange themselves into a surprisingly limited number of specific configurations to encode the information necessary for that self-replicating chemistry to work as well as it does? While those investigations are beyond the scope of this series, I do hope to get to them eventually. Relevant to this series, though, is the question, with the exception of hydrogen, why do any of them exist at all? While George Gamow and his collaborators were able to show that they could create from the fundamental equations of physics, at least as they were known in the late 1930s and early 1940s, the two simplest of elements, hydrogen and helium, they could not produce anything more complicated than that. They could not explain where the oxygen, carbon, and nitrogen so prevalent in their own bodies came from, not to say anything of the more massive and complex metallic elements such as iron, copper, or zinc. Yet, even as they were struggling to build a universe that would produce a complete menu of 90 elements, Gamow's colleague and competitor, Fred Hoyle, was building on 20 years of work to provide the answer in a place no one had thought to look. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 45, The Stuff of Stars. To understand where we are going, we need to go back a bit to pick up some ideas that we've mentioned in previous episodes that we'll need to make things make sense here, if that makes any sense. The first thing is to remember is what the project here is. Gamow, Alpher, and another colleague by the name of Herman have managed to put forward not only the idea that the universe began as a very hot, very dense primeval fireball, but they've also managed to work out the various physical processes that would occur as such a universe expanded and cooled. They were able to talk about how the most fundamental building blocks of matter known at the time, protons, neutrons, electrons, neutrinos, and of course photons, along with all of their antimatter counterparts, would interact, and in time not interact, in order to create the matter that was sprinkled across an ever-expanding fabric of space-time. At the time when the universe cooled off enough for the energy, in the form of light, to decouple or stop interacting with the mass for the most part, Gamow and Alpher were able to show that the universe would be about 3/4 hydrogen, a bit less than 1/4 helium, and less than 1% of both lithium and beryllium, along with just a tiny little bit of an isotope of hydrogen that consisted of 1 proton and 1 neutron, known as deuterium. While the work was impressive, it couldn't produce any of the elements that were heavier than those. In scientific terms, it was a good start, but it left a lot of things unexplained. Because of this, there were those that felt that there were better alternatives to this idea for explaining the origins of the cosmos. None so popular as Fred Hoyle's steady-state expanding universe, that put forward the idea that matter was being created at a very, very slow rate so that the universe could expand and yet still look uniform without having to have come from a single point of origin. Now, Hoyle's going to be very important to our story today, but to understand why, we need to go back to the turn of the 20th century. It is at this time that the women of the Harvard College Observatory are beginning to create robust classification systems for the stellar spectra that Edward Pickering's astronomers were gathering. First it would be Williamina Fleming, then Antonia Maury, and then finally Annie Jump Cannon, who would see patterns of regularity in the spectral lines taken of the various stars, and thus classify them, at least initially, according to those patterns. What should be understood about this work is that it falls under the broad heading of developing a natural history, an organizing principle first suggested all the way back in the 1500s by Francis Bacon as a way to see underlying relationships. As was the case with the spectral classification schemes, it quickly became apparent that there was likely something that gave rise to the changing patterns of, say, the Fraunhofer D-line that was really quite interesting. What wasn't very clear, though, was what that thing was. At the time, astronomers' knowledge about the stars, other than they produced light, wasn't really very big. However, as the spectrometer and spectroscopy began to advance by leaps and bounds, men like James Keeler, William Huggins, and as we've discussed extensively, George Ellery Hale began to not only observe the lines of the spectra, they also created physical laboratories devoted to creating the conditions wherein the spectral lines could be developed or created on the Earth as a way of understanding the physical processes that produce them. It was in this way that Hale's observations of the solar spectrum, especially with respect to the sunspot, was so important. He showed how a new breed of astronomer that paired the observational and the experimental, soon to be known as an astrophysicist, could establish knowledge that an investigator working with only one of those two tool sets would miss. It was through these types of investigations that Hale and others established that spectral lines could be affected by the temperature and pressure of the environment in which they were created. They were also able to show that the sun and other stars were made of the same elements found here on the Earth. All of this took a lot of time and effort through the 1890s and 1900s, in no small part due to the fact that no one was really sure how spectra were produced or why the various patterns that were in those spectra were observed, either in the individual elemental spectra themselves or in those spectra gathered from the sun and stars. And to be clear, this was just one of the problems that faced the very new field of stellar astrophysics. I don't think it would be an exaggeration to say that in 1910 there were more questions about the nature of stars than there was solid knowledge about them. There were questions about their composition. What were they made of, and in what proportions? There were questions about how they produced the energy that they then released in such enormous quantities. And then there were questions about how they were formed, how they lived, and how they died, assuming that these processes did in fact take place. In other words, to borrow from biology, how did they evolve? Which, as author Stephen Jay Gould once pointed out, is probably a term more appropriate to the process governing stellar life cycles than to the diversification of species as described by Darwin and others, that, as a process, is a good bit more lurchy and uneven, less evolutionary and more revolutionary, perhaps. In any case, it is to each of these questions we must briefly turn to help set the stage for what will take place in the 1920s and beyond. When looking at stellar composition, the informed consensus in the first decade of the 20th century was that the sun, and by analogy the rest of the stars, were not only made of the same things as the Earth was, but that it had those things in roughly the same proportions. In other words, any differences seen in the sun's spectrum was due to the much higher temperature of the solar environment, understood to be near 6,000 degrees Kelvin as opposed to the Earth's 300 degrees Kelvin. The next question had to do with how the sun produced its energy. In the 1860s and 70s, William Thomson, also known as Lord Kelvin, and Heinrich Helmholtz had derived a mathematical model that said that the sun generated energy through the process of slow gravitational collapse that could produce the stunning amounts of energy our closest star emitted for periods on the order of tens of millions of years. While this was initially thought to be a sufficient time, by 1910 it was clear that the results of geologic dating and paleontological research into the development of life on Earth were suggesting that the planet had been in existence for 1 billion or more years, with evidence of plants which use photosynthesis being a part of the ecosystem for much longer than the time frame the sun would have been able to shine, even under the most optimistic of the Kelvin-Helmholtz models. Finally, while the process of stellar evolution was still fairly speculative, a number of models had been developed that all had the stars being more or less the same mass, at least in the initial models, and progressing through the various colors of the spectrum based on a process of beginning hot and blue and then cooling through various spectral classes until they became red. In the years between 1905 and 1910, Einar Hertzsprung and Henry Norris Russell had taken the data being generated at Harvard and created a new type of diagram that plotted how bright the star was against the spectral class or color, that showed that most stars were found along a line from the very luminous blue stars in the upper left-hand corner of the diagram to dim red stars in the lower right-hand portion of the chart. Hertzsprung had also shown, working with the spectral classifications of Antonio Murray, that there were stars in the redder portion of the spectrum that were significantly more luminous than those on the main line or sequence. These stars he dubbed giants. This suggested a more complex evolutionary path for stars than the simple start hot and blue and cool to dim and red path that many put forward prior to that time. Russell, among others, suggested that there had to be an initial collapse phase of stellar evolution, wherein the star formed from a collapsing cloud of interstellar gas and dust. This initial collapse would account for Hertzsprung's giant stars without having to modify the core portion of the dominant evolutionary model. As a final point, while we have spent most of the time in our podcast here looking at the more cosmological advances in the years beyond 1910, beginning with Shapley and ending with Gamow, it should be understood that these lines of research represented only a small fraction of the total work being done. While Einstein's work in relativity and Hubble's discoveries at Mount Wilson would be trumpeted in the press after 1920, many astronomers and astrophysicists complained that such work only accounted for 10% of the total scholarly production of the great facilities that were coming online. In contrast to the public perception, most of the work being done at the big telescopes at Mount Wilson and the Lick Observatory was in the field of solar or stellar astrophysics. And in 1913, a young Danish physicist would pry open the door to look a bit more closely into the atom in a way that would reshape many of the assumptions regarding that work in stellar and spectral astrophysics and the nature of stars. The young Dane, of course, was Niels Bohr, and his discovery was that spectra produced by the various elements were made by electrons transitioning between energy levels around the nuclei of the atoms. Upward transitions would absorb energy and were responsible for the dark line emission spectra so often seen, while downwards transitions emitted photons of light at certain characteristic wavelengths and created those emission spectra we've discussed. This discovery, along with subsequent work done by Bohr and his collaborator Sommerfeld, offered astrophysicists a mechanism to understand the observations they were making, as well as something of a theoretical framework to guide their experimentation. Now, as part of this work, Bohr had spent a good bit of time at the Cavendish Laboratory of Cambridge University working with the team of Ernest Rutherford. Among the undergraduates studying physics and astronomy at Cambridge at this time was the talented young Cecilia Payne, whom we featured in an earlier episode of this series. As we discussed there, Payne realized that her prospects for advancement in the scientific culture of England at that time were limited, and so in 1921 she left to travel to the Harvard College Observatory to work towards earning a PhD under its new director, the progressive Harlow Shapley. Over the course of the next 4 years, Payne would use the knowledge she had gained regarding electron transitions and spectra while studying at Cambridge to build on the work of Meghnad Sadah regarding the spectral line characteristics, as well as calculations on elemental absorption done by Arthur Milne and Ralph Fowler. While the details of this research are probably a bit too esoteric to go into any detail here, let me see if I can outline all of that just a little bit. When you have an element, an atom say, in an environment, the wavelengths of light it absorbs and emits depends on the specifics of the electron configuration within the atoms of that element. That configuration can depend on various things, but most importantly, it depends on the temperature and pressure of that environment. For our purposes, the high temperature environment of the sun's surface and atmosphere can cause a process known as ionization to take place, where one or more electrons can be removed or stripped from an atom, thus changing the electron configuration and the element's spectrum in certain ways. Prior to Sadah's work, these changes could only be observed directly in a laboratory and often in somewhat inexact ways. What he did was develop mathematical models that would show how the ionization of certain elements, or even changes in the temperature or pressure of an environment, would change the electron configurations in the atom and thus the spectra produced. What Payne was able to do is use this work, along with the strength of the various absorption lines in the sun's spectrum, to calculate just how much of each element was present in the sun. first publishing her work in what Otto Struve called, quote, undoubtedly the most brilliant PhD thesis ever written in astronomy, end quote. Payne was surprised to show that while the sun was indeed made of the same elements found on the Earth, the amount of each element was vastly different in the sun than it was on the Earth. While the Earth is comprised mostly of oxygen and silicon, the sun is made up of 71% hydrogen, 27% helium, and about 2% everything else. Moreover, Payne was able to explain why the spectra of the different classes of stars changed as a function of temperature by assuming that they too had similar compositions to the sun. In short, due to Payne's work, the universe now became a place where the simplest of elements, hydrogen and helium, dominated. While it would take another 4 years before the rest of the astrophysical community would come to accept her findings as being true, by 1930 it was well understood that stars were made of hydrogen and helium and that their spectral characteristics were due to their temperatures, thus reinforcing the use of spectrographic parallax as a way to determine the distance to a star. While this was truly a major development in our understanding of stellar composition and structure, it was not the only one. In fact, in the years Payne studied at Cambridge, the chair of the astronomy program there, as well as the director of the Cambridge Observatory, was beginning to solve additional puzzles related to various processes associated with stars. Arthur Eddington had been named Plumian Chair of Astronomy at Cambridge in 1913 after a successful tenure as chief assistant to the Astronomer Royal. The Plumian Chair was supposed to be devoted to observational and experimental work in astronomy at the university, but when George Darwin, son of Charles, and Chair of Theoretical Astronomy at Cambridge, died unexpectedly in 1914, Eddington successfully lobbied for the consolidation of the two roles under his chairmanship, as well as accumulating the post of director of the observatory. And in that role, he began moving the work done at the university away from astronomy and towards astrophysics. As a Quaker and thus a conscientious objector, Eddington was exempted from service in the Great War and so was in a position to engage in the discussions related to Einstein's theories of relativity. In 1919, he would lead the expedition to Prinkeep that would provide the first new observational evidence during the solar eclipse there in support of Einstein's general theory. As was the case with many astrophysicists at this time, Eddington's interests were rather varied, and so, along with his work in general relativity, he also did work on a number of other projects, including one wherein he focused on finding stellar masses by examining the orbits of binary stars in some detail. This was actually very important work because, as we said earlier, the assumption for a very long time before this was that stars were all more or less uniform in terms of a number of their properties. And as an aside, one way in which one could view research in stellar astrophysics from the past up through this period, maybe even a little bit longer, is through a sort of lens where each of the assumptions regarding the uniformity of physical characteristics were eventually shown to be wrong. You sort of look at, we showed that this was wrong, and that represents this development, etc., etc. For example, in 1862, observations of Sirius had shown that the star had a dim companion that was roughly 1/5000th as bright. Now, if the two stars were known to be the same distance from the Earth, which was in fact the case, that meant that the dimmer star had to be a lot less luminous than the brighter star was. In 1912, Henry Norris Russell had undertaken the project of determining the masses of stars in eclipsing binaries and found that the less massive the star was, the further down the main sequence of the HR diagram that star tended to be. And Eddington built on this work in two ways. First, in 1916, he began to develop models of the internal structure of stars, starting from work done by Carl Schwarzschild and R.A. Sampson, that showed the mechanisms most likely responsible for getting energy from the interior of a star to its surface. To make these models easier to use, Eddington initially considered only Hertzsprung's giant stars so that he could treat the gases as being quote-unquote perfect. This allowed him to come up with a central temperature of those stars of about 5 million degrees Kelvin, and then from that to determine the theoretical luminosity for each star. The outcome of his work led him to show that a star's luminosity depended only exclusively on its mass. In other words, the more massive a star was, the brighter it was going to be. Now, this was a very interesting result, but it was just merely a theoretical calculation. So what Eddington did was that he went back and he got data for as many real stars in binary systems as possible. Now, as we've discussed in the past, these stars are going to obey Newton's laws of motion and the universal law of gravitation. And so, with good orbital numbers, such as, say, the period of revolution, it's possible to determine each star's mass with a pretty high accuracy. Once that's done, Eddington was able to use either trigonometric or spectroscopic parallax to determine each star's luminosity. What he found was that even for stars that were on the main sequence, his mass-luminosity relationship worked amazingly well. This work would be published in 1924, and it would show that unless stars lost a lot of mass during their lifetimes, something that was not observed either in the Sun or in any other nearby stars, they would not evolve by moving down the HR diagrams as the, at least at that time, accepted models of stellar evolution suggested. In other words, the ideas related to how stars worked were in need of serious revision. As Eddington and Payne were making their discoveries, the question of the ages of stars was becoming more and more of an issue. The question was, if a star like the Sun really was a very hot ball of gas, how could it produce so much energy as long as it needed to? In other words, as long as the geological and biological evidence suggested it would have to. Now, as we said, prior to this point, the physicist James Jeans had used the Kelvin-Helmholtz relationship to show how the collapse of a cloud of interstellar gas and dust could form a star. And with this, he was able to show that the larger the mass of the collapsing clump was, the faster that process of collapse would take place. But what wasn't clear was how the star would produce energy once this process had created something about the size we see the stars being throughout the galaxy. In other words, Jeans could use the Kelvin-Helmholtz relationship to get stars to form, but what he couldn't explain was how they actually continued to shine for the time periods it was thought they needed to. Now, one idea was that a star might be able to add mass in some way. But this, as soon as it was sort of proposed, was almost immediately discarded, as it was determined that the rate at which this mass addition would have to happen would actually alter the mass of the star so much that the orbits of the planets would have changed in the time since Tycho Brahe had begun making truly high-quality observations of those orbits. And so you're still left with the same question, and it's here that Eddington once again showed his range as sort of a astrophysicist of all trades. I've had a bit of difficulty trying to pin down a date as to when he first came up with the idea that we're about to talk about, with some sources suggesting a date not long after the Prinkeep expedition, while others saying that it was after the publication of Payne's thesis. But sometime between 1920 and 1927, and I tend to lean towards the latter end of that range, he began to consider an altogether new and unheard of process of energy production, the fusion of lighter elements into heavier ones. To understand this, we need to say a few words about the theory of special relativity and work being done in atomic physics. Einstein had shown with special relativity that there was an equivalence between mass and energy, that energy could be converted into mass in some physical processes, while in others, mass could be turned into energy. This, of course, is encapsulated in the famous E equals mc squared relationship, but it rests on quite a bit more physics than that. In his general theory, Einstein expanded on this by showing how such processes fit into the larger space-time framework. The other contributing piece of this idea was that the nucleus of a helium atom had slightly less, or does have slightly less, mass than the pieces that make it up would have if they were each all by themselves. This work, an outgrowth of the increasingly precise measurements being made of atoms in the field of atomic physics, showed that the mass of a proton is 1.0073 atomic mass units, and the mass of a neutron is a slightly more massive 1.00867 atomic mass units, or what we'll just call AMUs from now on, if that's okay. A helium atom has a nucleus that is made of 2 protons and 2 neutrons, and so if we add those masses up, we should get 4.0319 AMUs. However, when that mass is actually measured, the number is really only 4.0014 AMUs, a difference of just a little bit more than 0.03 atomic mass units. So, where did that extra mass go? Eddington's insight was to recognize that if the sun was a huge ball of hot gas, the temperatures and pressures in the center might be enough to force protons that made up the hydrogen nucleus that, the sun was basically all made of. It was enough to force those hydrogen nuclei close enough together that they would fuse in some way to make helium. And if that were the case, the mass lost in this process would be converted to energy that, after a long process of travel involving absorption and re-emission and all sorts of things that started in the core and worked its way out to the surface, would then be radiated out into space. Now, this is a big jump, but if it's true, Eddington realized it might be able to explain how the sun could produce energy for as long as the data suggested it would have to. Now, he knew the energy output of the sun, and so he calculated the amount of hydrogen that would have to be converted into helium. And the first thing he found was that about 4 million tons of matter every second would have to be turned into energy. And this amount would require that 600 million tons of hydrogen would have to be converted into helium every second. An equivalent, to 2 times 10 to the 16 or 20 times, a billion trillion tons of converted hydrogen every single year. Now, this seems like a really enormous number, and this is where we'll use scientific notation to make the number at least a little bit more understandable. And so we oftentimes will say it's 2 times 10 to the 16 tons. But what Eddington knows is that the mass of the sun is about 2 times 10 to the 27 tons of material. And so what he realizes is that if he does the calculations, that the sun's only going to fuse about 10% of its hydrogen every 1 billion years. That's amazing to think about. And thus, it would last somewhere around 10 billion years before running out of fuel. Now, an important note is on order here. Without Payne's determination of the composition of the sun as being mostly hydrogen with some helium, it's pretty unlikely that Eddington would have ever gone very far with this idea. And so, his discovery really rests on top of hers. What's also important to note is that while Eddington has had a good idea, and a pretty good one at that, he doesn't really have anything more than that. He doesn't have an idea of just how such a process of fusing 2 protons together might take place. In fact, when he does the earliest calculations to see if there was a way to get those 2 hydrogen nuclei, or, really what those are protons, to overcome their mutual electrostatic repulsion, remember here that like charges repel just like the north ends of magnets repel, it was seen that there was really no fusion because the temperatures weren't going to be high enough at the center of the sun. Eddington's own calculation found the temperature at the sun's core of about 15 million degrees Kelvin at a pressure of about 123 million times the Earth's atmospheric pressure. But unfortunately, this wasn't enough to get those protons squeezed close enough together that they would fuse to other protons to form something else. Nevertheless, even with this deficiency, fusion seemed to be the only way to get the sun to shine for long enough to see the things in the geological record of the Earth that were being seen. There's this wonderful story that when Eddington's colleagues rejected his model as being too cold to produce fusion, thus invalidating his idea, he is reported to have said, or at least to have recommended, that they, quote, go and find a hotter place, end quote. In other words, Eddington was pretty sure of his ideas as they explained too many things too well to be wrong, at least in terms of the broad brushstrokes. Fortunately, his idea didn't really sort of have to spin in the wind very long before a solution to that problem appeared. As you may recall from our last episode, in 1928, George Gamow, while doing postdoctoral work, calculated the quantum tunneling mechanism that was responsible for the process of radioactive alpha decay of massive nuclei such as uranium. A year after that, the British physicist Robert Atkinson suggested that the reverse process was also possible, and, if applied to proton fusion, could explain how two protons get close enough to combine at the temperatures Eddington suggested. It wasn't a complete solution by any means, but it did open an avenue of research for investigators to follow. And follow they did. At least eventually. A funny thing happened on the way to the solution. Atkinson immigrated to the United States shortly after doing this work, and he was followed in 1933 by George Gamow. Gamow's departure coincided with the rise of fascism in Europe, and soon men like Edward Teller and Hans Bethe would follow, fleeing the repressive policies of those Central European governments that embraced the new political ideology first put into place by Mussolini in Italy. It would take a while for these physicists to settle into their new surroundings and reestablish the research programs. But when they did, they found that things weren't as straightforward as just sticking together 4 protons and calling it helium. So, in 1938, Gamow put together the 4th Washington Conference on Theoretical Physics, with the stellar energy problem being foremost on the agenda. Hans Bethe was in attendance at the meeting, as was Edward Teller and his graduate student, Charles Critchfield. Critchfield had been working with a series of nuclear reactions using the results of Enrico Fermi's work on the weak interaction that, while intriguing, still had some problems. Bethe, on the other hand, had been working with a different set of processes that would use carbon as sort of a nuclear reaction catalyst that would build up an atom of carbon from its original state through nitrogen and then oxygen until the addition of one additional hydrogen would cause the oxygen atom to split into a carbon atom and a helium atom. Known as the CNO cycle, Bethe's process worked, but it required higher temperatures than were thought to exist at the center of the sun. And so it was kind of thought that maybe this wasn't the process that was producing energy at the center of the sun. The two men found much in each other's ideas to recommend them, and so began a collaboration to see if they couldn't resolve the difficulties each of their approaches had. Within a few months, they published papers on their 2 chains of nuclear reactions. Critchfield's called the proton-proton chain, and as we've said before, Bethe is called the CNO cycle. They also determined that while the proton-proton chain was the likely source of energy in stars like the Sun, stars with higher masses and thus higher internal temperatures would be able to use the CNO cycle, provided one could determine where the carbon had come from in the first place. This work was, to a great degree, the basis of the work Gamow would do in the mid-1940s on his primeval fireball that generated the mix of elements that it did. Unfortunately, it didn't really explain how you could produce elements as heavy as carbon. The other issue here was that the work was really completely theoretical in nature. However, as soon as the papers were published, the physicists led by Charles Lorentson at the Kellogg Radiation Laboratory at the California Institute of Technology began to take up the task of seeing the processes that would take place in these sorts of things. The work being done by Lorentson, along with the father-son team of Thomas and Willie Fowler, was to take beams of highly accelerated protons, i.e. hydrogen nuclei, and shoot them at carbon and nitrogen atoms to measure just how often the hydrogen nuclei would be captured. Realizing that the Bethe-Critchfield papers meant that their experiments could be applied to processes that might take place at the core of the Sun, they shifted their research accordingly. Soon enough, they began to provide hard experimental evidence that not only backed up the theory produced in those 1939 papers, but they also provided evidence for another advancement that would be crucial to our story. During the Second World War, the British astrophysicist Fred Hoyle was working on a series of problems related to this process of nucleosynthesis, as it is called, or this building up of elements in the middle of stars. Like everyone else, Hoyle was hoping to continue the process of creating more and more massive and complex elements by fusing together less massive ones, as had been the case with hydrogen being fused in to form helium. However, like everyone else, every time he tried to make stuff bigger than helium, he found that it was too unstable and it fell apart too quickly. He could make things actually all the way up to boron, but after that, things just never happened. However, in 1945, he hit upon a way to fuse 3 helium atoms together to form a carbon atom. It involved the helium atoms being in an energetically excited state, something that required a lot of helium in a very hot and dense environment. Something that would have already passed by in Gamau's attempts to synthesize heavy elements in the primeval fireball, but an environment that Hoyle would have found all over the place in the middle of the sun. While it would take 5 years to figure out all of the details, Hoyle would eventually travel to the Kellogg lab in 1953 and, working with Willie Fowler, would show that not only was such a reaction possible, but also that other, heavier elements could be made inside the cores of stars as well. Hoyle's 2 papers, the first in 1946 and the second in 1954, would set forth the fundamental ideas and processes by which the elements, at least up to iron, could at least theoretically be made inside of stars. A few years later, a seminal paper on all of this, with all of the details worked out, was published by Hoyle, Fowler, and the husband and wife team of Geoffrey and Margaret Burbidge in the 1957 Reviews of Modern Physics. In this work, the puzzle of nucleosynthesis was more or less solved, and the question posed in the introduction to this episode was answered. The stuff we are built out of was made in the cores of stars. As Carl Sagan, among others, has said, we are star stuff. From the calcium in our bones, to the iron in our blood, to the carbon that forms the backbone for most of the molecules that are dynamically knitted together in every instance of our existence. We are built out of atoms that once resided in the interiors of thermonuclear furnaces that forged the very matter of our existence. Now, to be clear, this is not the entirety of that story. While the B²FH paper, as it's known, showed how elements were made, it also showed that for elements heavier than iron, the conditions needed to create them would not exist in the centers of stars. It would only be after the work of Subrahmanyan Chandrasekhar on degenerate states of matter and supernovae that the mechanisms for the production of even heavier elements would be fully understood. Additionally, as these advances were being made, so were those associated with the understanding of the process of stellar evolution. While fascinating in its own right, that story, unfortunately, is not our story today. Instead, it will have to wait for another time, other than to say that with Eddington's work, it was soon established that stars spend most of their lives on the main sequence of the HR diagram, fusing hydrogen into helium, having collapsed from that cloud of gas and dust, and then, after a time determined by their mass, they would expand to become giants or supergiants before ending their existence either as planetary nebulae and white dwarf stars, as a supernova and a neutron star, or as that most exotic of relativistic objects, a black hole. For our story, though, The long quest to understand stars has brought us to a place where one of the major problems with Gamow's primeval fireball can now be addressed. Ironically, it was Hoyle's solution to the nucleosynthesis problem that provided the answer to one of the biggest issues with the theory that the Brit called, derisively, the Big Bang hypothesis. Now, instead of having to make all of the elements in the initial minutes of the universe's expansion, Gamow could leave that process to the stars, a result that would be confirmed by a German immigrant by the name of Walter Bethe. It would be Bethe's nearly sole possession of the 100-inch Hooker telescope during the years of World War II that would also solve another of the Big Bang's problems, and that would be the age paradox. As we wrap this episode up, let me say thanks to Steve Guerra for the introduction to the show and encourage you to go out and give his podcasts a listen. It can be said, I think, that at least up to the contemporary period, no institution in the West has had more influence and has been more consequential to the West's development than that of the Papacy, something that we've talked about in some of the earlier episodes of this series itself. Also, if you'd like to find other ways to interact with our show, you can find us out on Facebook by searching on the podcast name. You can also head over to our webpage, thescientificodyssey.typepad.com, to check out additional information that we often post about the episodes. Next week, I'd like to take a bit of a detour and do a biographical episode on Arthur Eddington. He was and is one of the most important figures in science in the period leading up to World War II, and it behooves us, I think, to spend a little more time discussing his life. So until then, full sails on your journey.